Welcome everyone to our exciting webinar on the launch of the Treble simulation platform. My name is Acoustics. I'm a UX developer here at Treble, and I'll be your moderator for today's event. Today we are thrilled to introduce you to Treble, a new cloud-based, wave-based sound simulation platform that is going to revolutionize the future of acoustic simulation and spatial audio. We do encourage you to ask questions throughout the webinar by using the Q&A feature in Zoom, and we'll do our best to address your questions during the Q&A session right after the keynotes. Please note that this webinar is being recorded and a copy will be sent to all registered participants. So, we have two outstanding speakers lined up for you today. First, we have Dr. Cheol-Ho Jeong, an associate professor of the Technical University of Denmark, who will provide an overview of room acoustics and room acoustic simulation, its challenges and its opportunities. Our second speaker is Dr. Finnur Pind, the CEO and founder of Treble Technologies. Finnur will be giving us an inside look at the Treble sound simulation software platform and its capabilities. So, without further ado, Cheol-Ho, the floor is yours.
Hi there, my name is Cheol-Ho Jeong. I'm from Technical University of Denmark, and I'm going to talk about room acoustic simulation. But first of all, I want to congratulate the team Treble on this amazing milestone of launch of Treble software. Yes, you see this picture, and we tried to estimate the room acoustics via simulations. And the human race has been very enthusiastic about creating nicely sounding space like this one. And basically the acoustic condition in a room is determined by three different factors: the geometry of the space, and the dimension of the space, and the material property at the boundary surfaces, and sound objects inside the space. Now we know how acoustics and noise affect the human perception and our well-being in buildings, and we are spending a lot of time indoors these days, and of course the room acoustic condition is very important. On the left we have a picture of the classroom, and this classroom, for example, classroom with very good acoustics make the students happier, they focus better, they learn more, and they behave better in the end. It's basically similar in offices like this, and this kind of nicely sounding offices make the people collaborate better way, and they are having less stress in this kind of space. So it's important to ensure good acoustic condition in buildings, and also we try to renovate the acoustic conditions in buildings, and we use a lot of acoustic simulation for that. We also use acoustic simulation for sound reproduction. So sound reproduction means that we don't have the space right now, but we could simulate the space and bring it to a lab like this picture, and which has a lot of loudspeakers, so we could actually reproduce the sound field. We also create some audio signals using acoustic simulation. For example, some audio signals in movies or games, video games. Last but not least, we use a data-driven approach a lot these days, and acoustic simulation has a potential to generate very good quality training data for a data-driven approach. And there's one assumption. The simulation must be very fast and accurate. And to be honest, we haven't been very successful in both aspects. Some simulations are really fast but not very accurate, and some simulations are really accurate but not really fast. I want to talk about the pressure-based and energy-based simulation in this talk. And basically, pressure-based simulations are predicting sound pressures. And many of the numerical, or all the numerical method, all the wave-based simulations, that's pressure-based. We calculate the pressures. On the other hand, many geometrical acoustics techniques, they are energy-based. Of course, there are some pressure-based geometrical acoustics techniques. So on the left, you see the sound propagation from a source, and there are two different colors, red and red and blue. Red means sound pressure is positive, and blue means sound pressure is negative. So we have kind of phase information in this kind of pressure-based simulation. And the sound is all over at any time. If you look at the picture of the energy-based simulation, we have approximate like wavefront, but the wavefront is not continuous. So we have a very discontinuous wavefront and sound field, and we don't have the phase information in this kind of simulation. So what is lacking in the energy-based simulation are diffraction and interference. I will go into those things a little later. Geometrical acoustics has really many good features. I mean, it's really fast, and it actually calculates the angle of instance, and it also visualizes the sound path very nicely with straight rays on this picture. But it is only the particle property of sound. And as Einstein mentioned, we have two contradictory pictures of reality. Separately, neither of them fully explain the phenomena, but together they do. So we want to combine the wave nature and the particle property of sound in acoustic simulation, and because they are complement each other. So diffraction. So this is a very, very simple setup, and this is a geometrical acoustic simulation. And we have a sound source far away from this structure here. And this is the sound source, and these are the receiver positions. We have a bunch of receiver positions at different angles. And from this angle to this angle, we have a direct sound and reflections. So you could actually see two different pulses. Like this is indicating direct sound, these are reflections. From this angle to somewhere, this angle, you have only the direct sound. And above this angle, there's no sound using geometrical acoustics. So we have a very discontinuous sound field. And this is actually indicating the impulse response from all the angles. By adding single diffraction and double diffraction, and by summing geometrical acoustics and those two diffraction components, we actually make the sound field very, very smooth and continuous. And this is the true picture, or more realistic in our life. So there is a way to add the diffraction component into the geometrical acoustic simulation. There is actually a better way. So when we are calculating this wave equation, numerically solving this equation, then we inherently have the diffraction in the solution. So Treble actually compared their simulation, DigiFM simulation, discontinuous scalar finite element simulation, against the brass measurement, which was measured by TU Berlin and TU Aachen some years back. And they actually recreate the wave nature, wave behavior of this measurement setting on the left very nicely. And the peaks and dips are pretty well matched. And those researchers, the German researchers from TU Berlin and TU Aachen, also made a round-robin test, and they compared the commercial geometrical acoustic simulation A, C, D, E, F against the measurement. And those geometrical acoustic simulations are struggling to match the measurement because they are energy-based simulations. The second thing I want to talk about is the wave interference. And we all know that interference is a very important phenomenon in sound behavior in rooms. And interference basically means that we have some frequencies like this one and this one, which have higher sound pressure level than at the neighboring frequencies. And at this point, at this frequency, the sound is behaving like this one. That's the longest dimension of the space, and the sound pressure is maximized at the boundaries, but the sound pressure becomes zero. So sound pressure can be zero because of the phase cancellation, or the cancellation of the sound due to the phase. So that's really nice picture of this pressure-based simulation. And we made a simulation between we compared the two different simulations. One is pressure-based simulation, the other one is geometrical acoustic simulation. And this is a rectangular room with dimensions of 4 times 3 times 2.7 meters. So the first room mode must be appearing around 43 Hertz. And one of the simulations, yes, you could see that kind of peak. The other simulation, you cannot really see any peaks around 43 Hertz. Also, we did a lot of validations on DigiFam simulation. Validation means we measure the sound field and compare it to the simulated transfer function. So as you could actually see here, the measurement and simulation matches pretty well, and simulated transfer function by the DigiFam simulation. So what makes the pressure-based methods so nice or so accurate like this? That's the magic of the phase information. And there are two types of phase information. One is the propagation phase. And once the sound is propagating, its phase is changing. And as you could actually see in this equation, phase is changing as a function of exponential function of exponential function of jkx. So as sound propagates, we have phase information. And some method can take into this account. For example, numerical simulations or wave-based simulations. The second phase information is reflection phase. And we have a reflection shift on the boundary upon the reflection. And if we are injecting some nice boundary condition or phased boundary condition, we could actually take a reflection phase into the simulation. And there are a bunch of evidence that pressure-based simulation is really matching well with the measurement. And on the left, we have a study by So and Nelson from ISVR Southampton, quite a long time ago, 1999. They actually compared the shape, temporal shape of the impulse response of the measurement and phased image source method and the conventional energy-based simulation. And there's a huge difference between the energy-based and the pressure-based simulation. And Lam from Salford University, he compared the sound pressure level over the frequency. And this is pretty nice because we could actually see the room modes directly. So when we look at this figure closely, then we have the measured data, pressure-based simulation, and boundary element simulation, which is a numerical simulation, and energy-based simulation. And only the energy-based simulation is estimating the same pressure all over the frequencies, while the other measurement and numerical method of phased geometrical acoustics, they are having these nice patterns at low frequencies. So it's very clear that pressure-based simulation is very accurate. Okay, let's move on to the boundary condition. In this slide, I'm showing two graphs. So the black line is the pressure-based image source method, and the red dotted line is the finite element simulation. And the finite element simulation is basically the same in these two graphs. So what makes the pressure-based image source method so different in these two? That's the boundary condition. We inputted different boundary condition. On the top one, we use the angle-dependent and complex value, the pressure reflection coefficient, which has the angular dependency and also the pressure or phase information inside. When we are using random instance absorption coefficient, that's kind of angle averaged absorption coefficient over the angle. Then this doesn't have any angular dependency and it doesn't have any phase information. That actually messed up the simulation pretty much. So more precise input data is always good, of course. Let's move on to this little difficult thing, extended reacting boundary condition. And extended reacting effectively means that the surface impedance is changing with the angle of instance. And in this graph, the black line is the measurement, and the blue line is the locally reacting boundary condition, meaning that we actually use the surface impedance for the normal instance condition. And the red one is the simulated transfer function using the extended reacting boundaries. So it's clear that the extended reacting boundary is really good, and that was done by Aretz and Volender from TU Aachen. And in this, in the next graph, this was the sound pressure level calculation between the extended reaction and the local reaction made by Murray Hodgson and Waring from British Columbia. And you could see a huge difference between the sound pressure levels estimated by the extended reaction and the local reaction. And Pind also estimated or experimentally validated the extended reaction and the local reaction. And the local reaction is the blue line, which is far off from the measurement. So my message is we have to use pressure-based method, and we have to use more precise boundary condition. It could be pressure-based reflection coefficient, surface impedance, or angle-dependent complex reflection coefficient. Then we could actually include the phase information, all the phase information into the simulation. And for example, for using energy-based simulation with less precise boundary condition, for example, sound absorption coefficient, we don't have any phase information. And this is actually one of the conclusions from this round-robin test paper in JASA. They concluded that most geometrical acoustics methods generate obvious model errors. That's due to the simplified use of random instance absorption coefficient and the scattering coefficient. So the quality of the boundary condition really matters. And those geometrical acoustic simulations are missing or insufficient modeling of the diffraction because it's simply energy-based simulation. So it's very clear that we have to use more pressure-based and good boundary conditions. Let's talk briefly about hybridization. We have tons of simulation tools, and why not hybridize the simulation in time and frequency? And this plot is actually showing this is a valid range for stochastic time frequency model of reverberation decay above the mixing time, above the Schroeder frequency. So Schroeder frequency is one of the transition frequency from low frequency to high frequency. So it's pretty wise to combine some numerical wave-based simulation like DigiFEM at the low frequency range and use geometrical acoustics in the high frequency range, because the geometrical acoustics is much more faster than the DigiFEM. Actually, Treble combined the pressure-based ISM in the geometrical acoustic part. So they actually extended the accuracy somehow. But it's always a compromise. If you really want a fast simulation, then this part must be bigger than the DigiFEM. If you really push the accuracy, then the DigiFEM could actually DigiFEM could be used for up to 2 kHz, 4 kHz, very high frequencies. And I know there is a similar study, similar PhD project in Eindhoven Technical University by Treble and Martin Honig's, and they are actually developing a simulation tool by combining DigiFEM simulation, ISM in the early part of the high frequency, and diffusion equation at late part of the high frequencies. Okay, assume we have very good, very fast, very accurate simulation. What kind of opportunity we have as acoustician? So we actually don't simulate that many buildings in the design phase. So it's only the very important rooms or music halls. That's actually less than 5% of the buildings we actually build these days. And by using accurate and fast simulation, we could actually increase the amount of buildings to be simulated in the design phase. For example, like multipurpose halls or schools, we use conference halls or offices every day, so they are very important. And the restaurants, for example, there are some restaurants with horrible acoustics, and hospital sound is not really great, and we could actually somehow improve the acoustic conditions of those places. Maybe we could also use some AI systems labeling that this acoustics is okay and maybe this acoustics is not okay. And this is very important because many architects, they draw something and they send it to acoustician. They have to wait for 2 days, or 3 days, or a week to get it confirmed by the acousticians. So the workflow is not great, but once the workflow is really good, I know Treble is actually focusing on one of the, at least I mean this aspect of seamless workflow between different people, to make enabling a better sounding world. So the beauty of simulation is that we could actually do some missing data imputation. So maybe you heard about this survivorship bias story. And during the World War II, American statisticians look at the damaged part of aircraft. And they realized that actually 26 engine damaged aircraft returned to the base, and 105 fuselage damaged aircraft returned to the base, or something like that. And we don't know actually how many are damaged and how many didn't return to the base. So due to this missing data, people are a little confused. But thanks to the simulation, they actually recreate this kind of data. So the power of simulation is to generate some missing data and do the missing data imputation like this. Then it's very clear that what is the chance of returning with the engine damaged, something like that. And if you look at those numbers, of course, the chance of engine damaged aircraft returned is less than 50%. Then, of course, we have to reinforce those parts, not the fuselage. So with complete data, we could actually answer to more meaningful questions. And that's the power of simulation. And the same in acoustics. So for example, we are very curious, what if we change the ceiling? What if we change the window? How is the noise and acoustics changes? And we could do all this kind of simulation without doing any physical changes. Opportunity number 3, synthetic data. We are living in the era of AI, and AI requires a lot of quality data. And we know that by doing a lot of measurement, we could actually get some real-world data, quality data, but it's very labor-intensive. So it takes a lot of time. It takes months or days and months and weeks. But using simulation, we could generate quality data in a day or 2. And acousticians actually knew that, because when we are making noise maps like this in big cities in EU, they are only using simulations. They never dare to send out people going out and doing the measurement for 24 hours for 365 days. That's impossible. So we are purely relying on the numerical simulation, acoustic simulation for those kind of noise maps. Opportunity number 4, we need sound simulation for multimodal perception. Sound is an important part of multimodal perception, so we need an accurate and fast simulation of acoustic space to do this multimodal perception evaluation. Okay, this is a second last slide, and you could actually see the benefit of simulation as a summary. Once we have an original model and send it to a fast computer or cloud, and when we change the boundary condition, that's basically AR. So if a company is claiming that they made a window which can reduce the noise level of the traffic noise by 20 decibel, you basically render the space and change the boundary condition of that window space, then do the simulation and make it, then simulate the acoustic condition or noise data. And you could actually hear the sound, use the headphone to hear those kind of AR, augmented reality condition, and compare the situations. We could do VR by changing the room geometry and the moving source, and we could optimize the acoustics by using simulations, of course. We could actually do speech enhancement using those kind of room simulation. It could be for the smart speakers or normal speakers like this one, or it can be also very useful in automotive industry like cars. And also hearing aid companies, they can also benefit from the room acoustic simulation. And also acoustic forensic or accident detection can be also done by doing a lot of simulation and make a surrogate modeling of the accident detection. So simulation has a really big potential in generating synthetic data for machine learning. So here's my conclusion. I think we need more and more pressure data than traditional energy parameters, and always keep that in mind, the accuracy and speed. We need accurate and fast simulation. And by having accurate and fast simulation, we could make digital models of buildings or urban street or robots or vehicles, many different applications. And we could generate a lot of synthetic data in a very short time for machine learning and AI studies. And we could make a sound simulation, sound stimuli for multimodal perception evaluation. Yeah, that's it, and thank you for listening.
Thank you, Cheol-Ho, for your informative presentation. Don't forget that you can ask questions in Zoom, and we'll get right to them after the keynotes. And that brings us to our second speaker. Finnur, take it away.
All right, hello everyone. It's great to be with you all here today. It's an exciting day for us at Treble Technologies, and we look very much forward to showing you what we have been building for the last couple of years. Here is the outline of my talk. I will first give just a brief overview of our company, Treble Technologies, and then a high-level overview of the platform that we are launching today. After that, I'll dive a little bit under the hood and show you some of the details of the simulation and rendering technology that we have that sort of powers the platform. After this, I will switch gears a little bit, turn off the PowerPoint and go over to the product demo and show you the platform and showcase its capabilities. And then after the demo, go back to the PowerPoint and very quickly talk about what lies ahead for Treble and a few words on pricing and support. All right. Treble Technologies is a startup that was founded in the summer of 2022, but actually our roots go back some years before that into academic research, mostly at DTU in Copenhagen. In 2020, we were just 4 guys, but now we are around 35 people, lots of passionate and brilliant sound nerds, and there is just so much momentum and fun at Treble these days, lots of fast developments going on. Our expertise is sound simulation and spatial audio, and our mission is to develop technology to make the world a better sounding place. Here you can see our fantastic team, the people that have been building the platform that we are showcasing here today. This is a diverse group of specialists within audio and acoustics, simulation scientists, data scientists, computational mathematics, and then over on software engineering side, all kinds of flavors of software engineers, high-performance computing, front-end, back-end, cloud, you name it, and then a few people on the commercial side too. We are based in Reykjavik, Iceland. The weather today in Reykjavik is pretty good actually, and there's sort of a hint of spring in the air, which is exciting. Okay, but Treble, the platform. We typically speak about Treble as a platform of virtual sound, meaning it's a software package that has functionality relating to sound simulation on the one hand, which is this concept of simulating how sound propagates in a 3D model. And then on the other hand, sound rendering, which is the idea of not just getting up graphs and numbers from the simulation, but rendering the simulation for listening, so we can experience how the thing we're designing will sound before it's built. When we started our company, we were exclusively thinking about the building industry. We wanted to develop a software package that enables engineers, consultants, architects, and others in the building industry to efficiently and precisely design and simulate acoustics as a part of building design. This absolutely remains a key focus for us, and the platform that we are launching today is perhaps most tailored towards this use case. But after we started, we also realized that having the ability to simulate sound in a fast and precise manner has use cases beyond building industry. So we have, for example, worked quite extensively in the, let's say, product or tech space, where people are simulating devices and interaction between space and device. Automotive industry, obviously sound is a huge component of automotive design. And then what might be called the metaverse, which is, in our interpretation, the idea of having some 3D virtual experience where you want the sound to be as authentic as possible. What we are trying to bring to the table with this new platform is summarized here in this slide. It's three things. First of all, which is perhaps the core of it all, new technology to simulate sound in a faster and more precise way than what's been previously possible. Second, a very strong emphasis on a modern, seamless workflow that is powered by the cloud. And third, last but not least, the idea of not just getting out graphs and numbers from the simulation, but being able to listen and experience the simulation in an audiovisual experience. The platform as it's built up today is summarized here. So the centerpiece is this web app here, which is the main user interface where people set up their simulations. They set material properties, sound sources, receivers, all kinds of settings. Then the simulations themselves run in the cloud. And once they're done running, results come back to the web app where users can view the results, analyze the results, look at graphs and numbers and things like that, but also listen and experience the simulation. We then have a live link connection over to SketchUp via our plugin, which enables a very seamless workflow and a seamless sort of iterative design process between the 3D modeling tool and the simulation tool. I will demo this in a second. Okay, let's now go a little bit under the hood and see what's going on. Of course, I can't go very deep in this short presentation here. If you are interested in more details, then you can, for example, download our white paper on the website or just reach out to us with questions. Our approach to sound simulation is a hybrid approach where we combine wave-based methods on the one hand and geometrical acoustics methods on the other hand. Wave-based methods are inherently very precise and they inherently capture complex acoustics physics phenomena such as diffraction and interference and phase. Geometrical acoustics is a good high-frequency approximation, which is so it's an appropriate choice for simulating the high-frequency range. And by combining these two approaches, we get sort of the best of both worlds. We get the accuracy and the frequency range we needed, and we get this at very short run times. This notion of the hybrid approach is perhaps not entirely new, at least in academia. It's been researched for some time. But it hasn't really found much sort of widespread commercial or practical application or usage because the wave-based simulations have always been so computationally heavy. And this is what we set out to address, and we're extremely proud to introduce our simulation, wave-based simulation engine, which is more than 100 times faster than what current state-of-the-art solutions on the market can offer. This means that now we can simulate a good portion of the spectrum wave-based. Smaller rooms, we can even simulate the full spectrum. In larger rooms, the sort of relevant frequency range where wave phenomena is most prominent, and have the runtime just be a handful of minutes. A few more details about the wave-based solver. So it is a discontinuous Galerkin finite element method, that's a tongue twister, formulation in the time domain. The benefits of this numerical method that we are using is that it has very high geometric flexibility, meaning that we can easily simulate complex geometries such as curved surfaces or fine geometric details. And then it has a very high parallel efficiency, which is a key component in what's enabling us to really accelerate these simulations so much. Third, last but not least, a very low memory footprint, which means that we can easily handle very big simulations. Okay, we're also extremely proud of our geometrical acoustic solver, which is also introducing new technology for high-frequency sound simulation. Our approach is a phased image source method / ray radiosity hybrid approach, which means that we can capture the phase of the simulation. We model boundaries with the phase shift included, and it's a pressure-based approach. So we actually capture the high-frequency acoustics very well, as we saw some examples from Cheol-Ho's presentation this morning. We also do angle-dependent absorption modeling, which improves accuracy at high frequencies, and state-of-the-art scattering modeling too. Now, as probably most of us here today know, the materials or the surface conditions of 3D models of spaces that we want to simulate the acoustics of have a huge impact on the resulting acoustics. And actually some research has shown that what people perceive to be the sort of weakest link in acoustic simulations today is the uncertainty relating to material modeling. So we have done or put in considerable effort to improve people's ability to model sound interaction with surfaces, sound absorption. And what we do here, what we're introducing, is the idea of modeling surfaces not in terms of just energy absorption coefficient, but modeling it via the impedance, which means that we capture both energy absorption and the phase shift. And we have carefully crafted a large database of materials which have sort of detailed impedances for all those different common material types which come with the tool. Additionally, we also do support traditional absorption coefficient input if you want to add a new material to the database, for example, where you have a data sheet with some absorption coefficients. And then we have an elaborate algorithm underneath which converts those absorption coefficients to surface impedance. And then last point here, we also are introducing the ability to model the extended reaction of porous materials. Porous materials are kind of the most common sound absorber that you will find in rooms. And by modeling the extended reaction, which is the angular dependence of the surface impedance, we get a much more precise simulation with when those materials are in play. We also do have powerful capabilities for modeling sound sources, where we enable both omnidirectional and directional sound sources like speech or human voice and loudspeakers. Our library of sound sources is growing fast and will be growing very fast over the coming few months. Now, when it comes to the auralization part, so we simulate high-order spatial impulse responses in our simulation, and then we use those to generate audiovisual auralizations. These auralizations are interactive, meaning that you can move the head and the spatial audio kind of updates in real time. You can be jumping between different positions in the space. You can compare different simulations, different material configurations on the fly. And this enables you to design soundscapes and assess sort of different design options in a very intuitive way. It also means that you can communicate acoustics design very effectively to clients and stakeholders and so on. As I mentioned in the beginning, our platform is entirely cloud-based and web-based. This comes with a lot of benefits. First of all, it's a key component in enabling us to really accelerate these simulations and enabling large-scale wave-based simulations too. Secondly, it allows us to do virtually unlimited simultaneous simulations, meaning that you can be setting up a simulation, firing it off, and immediately starting another one, even running hundreds or thousands of simulations in parallel if you want, for example, for some sort of parameter sweep or for generating data where you want to simulate a lot of rooms in parallel. The platform is entirely has a zero hardware and software footprint, meaning that your computer is not strained when you run a simulation and you don't have to install any software or anything to work with the platform. And then all kinds of nice features such as collaboration features, working with colleagues within your organization or across organizations, your history being backed up so you don't have to worry about losing some old simulations, and world-class security just like your online bank. And also, as I mentioned earlier, we have a live link connection to SketchUp, meaning that you don't have to be importing or exporting any files. If you modify the 3D model, then it immediately propagates over to the simulation platform and so on. And I will demo this in a second too. Cheol-Ho showed some very interesting benchmarks earlier today where he was comparing wave-based simulations against measurements and so on and seeing a very good match. So I won't go deep into this part here. I'll just show one quick benchmark example. This was done in collaboration with COVI, an engineering consulting firm, where they were analyzing the acoustics of this rather typical open plan office. And they carried out extensive measurements in the space and then used a beta version of the Treble platform to simulate it and compared the results. What they found was that the reverberation time of the room was very well predicted with the Treble simulation tool, the wave-based part of it, which covers the low to mid frequencies, whereas standard geometrical acoustics tool could not predict the true reverberation characteristics of the space. Okay, I will now switch gears and pop open the tool and let's take a look at how it's looking. Okay, so let's refresh this one. So to open the Treble platform, I go to app.treble.tech. First I have to log in. I've already logged in. And what I'm faced with here is an overview of the different projects that I've been working on. A project can, for example, be a school, and then a school building will have different spaces within the building which I'm designing the acoustics of. So for example, a particular classroom, another classroom, a meeting room within that school. Same for a hospital or office building or whatever. And today I'm going to play a bit around with this model here, this space, which is a part of this office building project. I go into the space here, and then I'm faced here with kind of different revisions of the geometry of the 3D model that I have been playing around with. So I will just open here one I've already uploaded, which is called the initial design. I gave it that name. Okay, and then I open the thing here, and I go into what we typically call the editor. In the editor, you can view the 3D model and move it around and things like that, and you can then set up your simulations and run them from here. So let's create a new simulation, and I'll just call it initial material configuration, something like this. And now the first thing that I have to do is I have to assign materials on the different surfaces in the space. When I prepared my 3D model, I divided some of the surfaces onto different layers to sort of facilitate the material assignment later. I can assign materials on an entire layer or on a surface within a layer if I want. And let's then open up the material library. As mentioned, it's a very extensive library of materials that we have sort of carefully crafted with impedance information and everything. And if I then open up a particular material, maybe let's open one interesting, something like this one, then I can open the detail view of it and see here the absorption characteristics, but also the complex reflection coefficient, which is related to the complex surface impedance. I also have some details about how this material was crafted. Okay, I can also create my own materials here, where I input absorption coefficients, and then I give it a category as well. And the category plus the absorption coefficients is used by this algorithm I mentioned earlier to convert the absorption coefficients into a physically plausible surface impedance. All right, but let's just try to assign some materials here. Let's start with a glass wall. That's a window material. So I will put a single pane of glass on the glass wall. I also have a layer here called windows, which is the sort of outer windows, and I'll put a double layer glass on that one. Okay, and then let's move to the tables here, maybe in the furnishing or the wood categories. And yeah, I have a material here called wood. Let's just put that one on. Doors, maybe this hollow core door material. Chairs, how about if we put leathered covered upholstered chair material on the different chairs here. And cabinets, maybe that's plywood paneling, 1 centimeter thick. And I think that's it for these two categories. The ceiling, let's start with the hard ceiling, so no limited acoustic treatment in this space. Let's say rough concrete here. And the walls, maybe they can be gypsum boards, something like this. The floor, let's use the search function here, put linoleum on the floor. And the monitors, how about if we just say they're 40% absorbing, frequency independent, as we see here. All right, next step is that I have to assign scattering coefficients. So the scattering coefficients are only used by the geometrical high frequency solver, which is sort of an indication of surface roughness. And the tool proposes some scattering coefficients based on the material that you've selected. In some cases that's a fine choice, but in other cases you might want to modify them a bit. And I'll just modify a bit here, maybe up to 0.6. Let's say the cabinets are also a bit more diffusive, tables as well, something like this. All right, now the materials are set. Next step is to set sound sources and receivers. So I will put a sound source in here. Let's give it a name. Cool source, and let's move it around. So let's drag it all the way over here. This is our first sound source. I can open the detail view of the sources, where I can select directional sound sources too, such as speech or given loudspeaker. As mentioned, we are growing our library of sound sources as we speak. But for this test here today, let's just use an omnidirectional sound sources. Okay, let's add a couple of more sources as well. Maybe one in the corner here and one somewhere in the middle of the space. Something like this. And then let's add a few receivers. Maybe first one here all the way in the corner, second one over here. Or let's maybe have that one be kind of sitting here by this desk. Should we put it a bit down? Something like this. And the third one in the corner. Something like that. Okay, materials, sources, and receivers are set. Last thing to look into is the solver settings themselves. We have kind of three presets here. A survey simulation is a fast but less precise simulation. Default, then the tool tries to propose a reasonable transition frequency from the wave simulation over to the geometrical acoustic simulation, taking into account the geometry and the materials that you have selected. And then we also do have advanced here, where we can sort of freely control how high in frequency we want to go with the wave solver, and some other settings as well. But I think we should just use the default setting here today. It's saying it's taking around a minute to simulate that. So I hit the run button here, and I start the simulation. Starting the simulation takes a few seconds. It's spinning up a machine in the cloud, provisioning resources, reading in the geometry data and putting it on all the GPUs that are running the simulations and so on. So this takes just a few seconds, and once that has begun, we can see the simulation starting to progress. Note here, I forgot to put names on the other two sources, so we have cool source and source 1 and 2. That's fine. So note here that we will see progress of the three different sources, because actually each source is a separate simulation, but the user doesn't really feel that you don't have to run them sequentially, they just run in parallel on the cloud. And now we see that this has started. Another thing that's very neat is that because this is cloud-based, it's not running on my computer, I can just close this thing and immediately start setting up my next simulation. And I can duplicate the settings of my previous simulation, so use that as a starting point and for setting up my next simulation. Let's say here, improved material configuration, some absorption in the ceiling. Something like this. Now I have everything that I previously set up ready to go here. I'm just going to change the material in the ceiling. Let's put some glass wool into the ceiling, maybe a 40 millimeter thick glass wool, so a rather commonly employed acoustic treatment, which has some absorption, particularly in the higher frequency range. I don't need to do anything else. Now it's suggesting that I simulate a bit shorter than before because the space is a bit less reverberant, probably because there's more absorption, but I just hit the run button and I'm ready to go. And now the two simulations are running in parallel. I can see the progress of all running simulations here in the sort of overview, all the recent simulations I have run and the status of current running simulations. And now it's telling me the first simulation is actually done. I want to show you the results of the two simulations in sort of together. So while we wait for the second simulation, I can show you a couple of things here. Let's go back to the first simulation. For example, in the advanced setting here, and I'm editing the simulation so it's giving me a warning, but in the settings here I can test how long the simulation will take as a function of how high in frequency I go. So let's just take a look at that for 1 second impulse response. For low frequency simulation, it's around a minute that it's suggesting here. But if we go higher in frequency, then the runtime increases, of course, and even higher to around 45 minutes for this particular space. But we can easily, clearly cover the sort of low to mid frequency range in practical runtimes with the tool here. Second thing I can show while we wait is a support portal here. If we have some issue or need some support, then we can just open the tool here, send us a message, and you will get a response and help very quickly. Okay. Now we can see the simulation is just about to finish the second one. I'm going to revert back so I didn't modify any settings of the first simulation, and we can start looking at results. I enter here the results view, and what I'm faced with here is two charts essentially. On the left here we see all kinds of acoustic parameters that we can analyze in the space. I can of course select different sources and receivers and so on and see how this varies. I can, we have reverberation time, early decay time, clarity, definition, center time, amplification or strength, sound pressure level, speech intelligibility as a function of the background noise level in the room, and so on. I can also look at the impulse response of the room and the narrow band frequency response, which is very precisely simulated here at low frequencies, which means we can analyze the modal behavior of the space too. Another thing I think is quite neat is that we can compare simulation results. So let's take these two simulations that I've now run and compare the results from them. And we see here with the improved material configuration, of course the reverberation time in the room decreases and the acoustics are improved. We will also see this in, for example, different energy decay curves and so on. The energy is decaying faster in the room when we have better or more absorbing materials. I can hit the download results button, which downloads all the spatial impulse responses and an Excel sheet with all these parameters and so on. Okay, this is sort of the graphs and numbers part of the results, which is very useful and interesting. But what's not less fun is to actually just listen. And then I go here into what we call the oralizer. Here I'm faced with a tool where I can create a sort of a soundscape in the model, and I can experience it and I can compare things on the fly. So here I have the 3 sound sources I put into the simulation. I can select sounds from our very extensive list of anechoic sounds to be playing from the different sound sources, and I can pull in here different simulations that I've run to kind of do A/B comparison on the fly, jump between receiver positions and so on. I'm just going to demo it now a little bit, and let's listen and enjoy. I'll start with just a sort of drum loop sound. It's a nice sound because it's so kind of percussive, so you can really hear the acoustics of the space pretty well. First I'll play the anechoic sound, and then I'll jump into the room and move around and change things on the fly and so on. Okay, I now go into the room. I'm moving the head, and the spatial audio is kind of updating in real time. I'm jumping between different positions, and I can compare the different simulations, the different material configuration. Clearly it's more reverberant in this initial material configuration. Okay, let's try putting in a bit more reasonable sounds here than just a drum loop. Let's try creating like an office soundscape. So I'll put some office atmospheric sounds here, some office chatter as well, maybe some classroom background as well. That's kind of similar. I'll play that here. Increase that a little bit. I can adjust these things on the fly. Maybe put the Atmos sounds a bit higher. Coffee machines going. And so on. So this is a way to analyze the acoustics in a more intuitive way, and also to be able to communicate the acoustics to someone who is maybe not so familiar with reverberation time graphs and so on. Okay, but let's now say that I wanted to improve the acoustics even further. I want to add partitions here between desks, and maybe this big wall here could use a wall absorber to get the reverberation time even shorter. Then let's open up SketchUp and modify the geometry here. Takes a second to start SketchUp. Okay, and I'll open an empty model like this. I'll open the Treble plugin here, and I can fetch the model that I was playing around with from the cloud, so I don't need to keep locally any files or anything like that. This was a part of the office building project of the second floor space, and let's fetch the initial design here. And then I get it into here. Here is my model with all the layers that I had previously defined. Now let's add a couple of layers. One we call wall absorber, and one we call partitions. Something like this. And let's start by drawing the wall absorber here. Something like this. Be sure to put that on the right layer, like this. And then let's draw in some partitions. Now you will have to live with my mediocre SketchUp drawing skills, but let's put a partition here. Let's say it's 80 centimeters high, something like that. Maybe it goes across here. Here's the midpoint, right? Midpoint. There we go. And draw it up here, 0.8, and across. Okay, now we have our first partition. It's on the partition layer. I'm now going to copy that and paste it to the other desks as well. Something like this. There we go. And the final one. Okay. These are the changes I wanted to make. Now I can just check the model that it's suitable for simulation. It is. And then I can upload it to the Treble platform. And let's say here, now with partitions and wall absorber. Upload this thing. It goes to the cloud, and I can pop it open here, and it takes me directly to the platform. Here I have not run a simulation on this particular revision of this geometry, so it's telling me I need to create my first simulation. I can do that, but luckily I can pull the settings of my previous simulation, so I don't have to set everything up again. And let's just say even further improved, call it this simulation. And then all of the settings that I had from before are set and good to go, except for the surfaces that were modified when I was modifying the geometry. So, for example, the tables here, they were a bit modified because I was putting the partitions on, so I'll have to reassign the material there. Wall as well, you know, most of the wall surfaces are untouched, but a couple are. I'll just reassign the whole layer here with this gypsum board material. Cabinets, what did we put? Plywood, paneling. And then the wall absorber, of course, let's put rock wool, 50 millimeter, maybe with a glass fiber surface as well. And the partitions, how about if we put that to be 25 millimeter rock wool with glass fiber surface. Okay, also need to double check that my scattering coefficients are correct. The ones that were affected will be reset, so something like this, and this one here. That's it. Now I'm ready to rerun my simulation with this modified geometry. Because I haven't run a simulation on this before, I need to estimate the runtime here. Or I could just hit the run button and then it would start, and then it would just first estimate and then run it, but I will show you the estimate function here. What's happening under the hood here is that a volumetric mesh is being generated of the space, the sort of finite element mesh that's used by the wave-based simulation. And here it's saying it's taking around a minute. Actually, I forgot one thing I wanted to do to improve the acoustics. In addition to the wall absorber and the partitions, let's put an even better absorber in the ceiling. How about if we put a suspended ceiling, maybe something like this one here. Suspended 200 millimeters, 70 kilos per cubic meter suspended ceiling, like a high performing acoustic ceiling. And then it's predicting, or it's saying I need to simulate 0.86 impulse response length. So this should be pretty good. Start this, and now we will wait for 1 minute while this simulation runs, and I think we'll just edit the video to come back in 30 seconds or so. Okay, now we're coming back here just 30 seconds later, and the simulation is just about to wrap up. There will also be a little bit of post-processing of the data before we can start looking at results. Let's just see that end here. And then what I'm going to do is I'm going to compare the simulation results from the 3 simulations that I've run, 2 of which were from the sort of previous revision of the geometry, and then 1 from this one, look at some graphs and numbers, and then oralize that, and then the demo is over. Okay. Processing, processing, processing. Here it's done. Okay, let's open the result view and compare those 3 material configurations that we were testing. The 2 others, were, as mentioned, are from the other geometry revision. One we called improved material configuration, and the other one we called initial material configuration. And indeed, as expected, the reverberation time has been reduced quite a lot compared, between the sort of okay material configuration and the good configuration, and much improved compared to what we had originally. And obviously we see that in other acoustic parameters too, that the sort of acoustic performance of the space has been improved. Okay, let's now go into the oralizer and listen to the space. So, as before, I can compare on the fly different receiver positions. I can move around the head, and I can compare different simulations, even from different models or different revisions of the geometry that I was running, as here. Let's pull in all 3 that we have run, and let's first listen to the anechoic sound, the drum loop. We get that here. And then I'll jump into the room and play a bit around. We clearly hear that the partition is doing its work, and also that the diffraction around the partition is modeled rather nicely with the timbre change that you can hear in the drum sound. And we can hear by removing the partition that the sound obviously changes. With the sort of more realistic office sounds. Real quick. What's this one? And classroom sounds as well. The speech source is this source here. You can kind of hear the spatialization or the localization effect pretty well if I rotate the head. And then I can. Okay, that was the quick demo of the Treble platform. Now let's go back to the slides and wrap this up. So I wanted to talk about 2 things here in the end, a little bit about the future or the roadmap, what lies ahead for us, and then just touch upon pricing and support. Starting with the sort of bit shorter term roadmap, let's say next 3 to 6 months, and then think a little bit longer, 6 to 12 months as well. So on the horizon for us is expanded results capabilities, the ability to generate these kinds of sound field animations within the tool, so you can really see how the sound is behaving in the tool, or create these kind of color map results as well. Also, sort of advanced post-processing capabilities, like going to extremely high order ambisonics. We're going up to order 16 now without problems, as an example. Sound source modeling, we want to add lots of sound sources to our database, but also add the ability that users can input their own sound sources or own arbitrary directivity patterns and then simulate them in the room to enable, for example, pro audio simulations or some kind of device room interaction simulation, including very precise low frequency simulations. A material generator. Here, this is a tool that enables you to kind of specify your own buildup of a material. Let's say 50 millimeters air cavity, then this type of porous absorber, and then 2 layers of gypsum board, or whatever. And then we have a sort of an algorithm that computes the impedance of this type of buildup, so you can model your unique materials in a more precise way than what's been previously possible. all kinds of collaboration features. An example is that you can create an organization which you can then create like a shareable link to, which you can share with your collaborators and, for example, your architect collaborator. So then you can set up like 3 different design options and ship them off in an organization that can be listened to by anyone. Also collaboration within organizations and across organizations. A Rhino integration is coming soon. I would say that all of these things that I just mentioned, we sort of have them working already, but we just need to kind of tweak them and get them nice into the front end and the user interfaces and so on. Okay, but if we look a bit further into the future, then this is the overview that we see of the Treble platform. The thing that we've been talking about today is this acoustic simulation suite here, and we will certainly continue developing that further, but we will also add additional modules to the platform, namely a synthetic data generator, a Treble API, and a connection to metaverse platforms. First, if I tell you a little bit about the sort of 6 to 12 month horizon for this one, then one major thing we're working on is a Revit integration. Revit is very widely used in the building industry, and we want to connect directly with this, automatically extract geometry from this, simplify it so that it can be run, so that you can run an acoustic simulation on it effectively. Synthetic data generation is an extremely exciting field. So audio machine learning algorithms, they require high quality data to be trained. This can be echo cancellation, beamforming, noise suppression, speech recognition, etc. And we have the ability with this advanced simulation technology, which is cloud-based, to run hundreds of thousands of high fidelity simulations and generate synthetic audio scenes which can be used to train these types of algorithms. And we're already offering this as a service, so we're working with some, for example, some of the large tech companies to provide this kind of training data for their development efforts. But with time, we want to deliver this more as a product so that people can set up these audio data set generations themselves. An API product is also in the pipeline, which enables people to integrate our simulation technology into their own solutions or into their own automated workflows and so on. And then a connection to metaverse platforms or gaming engines to enable even more immersive organizations and sort of 6th degree of freedom organizations, meaning you can move around the space freely and so on. So that was it for the roadmap. Last slide here, just about pricing, licensing, and support. We offer the platform as a subscription or using a subscription licensing model, meaning that people subscribe to the model and pay a monthly fee for access. This ensures that people always have the latest version up to date and that they get access to world-class support all the time. Anyone who's interested in trying the platform can do so for free for 30 days. So please reach out to us if you're interested in giving it a spin. And then we have sort of 3 license types here. A basic license, which is a single user license, a professional license, which is also a single user license, but with bit more cloud computing capabilities, let's say. And then an enterprise license, which is for organizations with 2 or more users. And we suspect that most people will go into the enterprise category here. And then what we do is we give a quote based on how many seats, how many users, and what the expected usage is. We're planning to price this, or we are pricing this in a price range which is competitive or even cheaper than existing solutions in this space we're working in. That was it for me. Thank you so much for listening, and I look forward to your questions.
Thank you, Finnur, for that fantastic presentation. I am sure our audience is eager to learn more about Treble and its unique capabilities. So we already have questions coming in, so why don't we go straight into the Q&A with Cheol-Ho and Finnur, and as we go through the questions, please feel free to keep them coming and we'll hopefully be able to address all of them. All right, let's just dive right into it. Okay, first question is from Ingo. Thank you for this wonderful event. What level of detail should furnishing have to provide reliable results? Is a spatial resolution in the 10 centimeter range sufficient? And what are your experiences with rounded corners, for example? Best regards to Reykjavik.
That's a great question. It depends a little bit on how high in frequency you go with the wave simulation. For traditional simulations where you have the low to mid frequencies, wave-based, and the high frequencies, geometrical acoustics, then indeed the sort of 5 to 15 centimeter range is a good rule of thumb. So kind of traditional acoustic models is a good choice. If you do want to do wave-based simulations up to very high frequencies, then perhaps it makes sense to use a bit more geometric details. And rounded corners and things like that, absolutely we can do that. If you want to do a detailed study of some curved surface or something like that, you can do the wave-based simulation for that. But if you want to do a more fast simulation where you do the hybrid approach, then you would discretize this a bit in this, again, 5 to 15 centimeter range. Yeah. Right?
Awesome. So, next question from Christian. Would it be possible to use this platform to design sound reinforcement system in some way?
A great question. This is, I would say, perhaps our top priority at the moment, to kind of increase capabilities for sound reinforcement system modeling. We do now have in the tool like a Genelec loudspeaker, for example, that you can model, but we're working really hard on enabling people to input their own arbitrary sound system and arbitrary directivity patterns, and sort of simulate the interaction between the room and the sound system in a very precise way. And, you know, the phase difference at low frequencies and designing loudspeaker coverage and things like that is coming. So 3 to 6 month roadmap is what we're aiming for here.
Awesome. That's exciting. Celia, have you considered other 3D modeling software packages like Rhino?
Yes, I guess that was maybe covered a bit later in the presentation after the question came. So indeed, Rhino is coming soon and Revit a bit further in the future, but we're working hard on that.
Next question from Hisan Song. Hello, I would like to know whether it could be applied for the multi-room scale, since there will be several flanking transmission and the transmission energy / pressure instead of just the reflection and refraction. Would it be considered later in Treble, or is it not a major concern for the space acoustics?
We were actually just this morning playing around with a little funny scenario where we had 2 rooms and then like a ventilation system connecting the 2. And you could actually simulate that really realistically, and it was kind of interesting to listen to this, to be in the other room and hear the sound go through the ventilation system. So in some sense the tool can already be used for this, but improved sound transmission modeling is also on the sort of short to medium term roadmap.
Okay, awesome.
I totally agree. It's really important to have this kind of functionality, sound transmission modeling in the right way.
Cool. So from Sylvan, does the tool only allow for point sources, or are volumetric sources also possible?
Right now we do point sources. But we have sort of under the hood already implemented capabilities to model more both surface sources and volumetric sources. And this is a part of Operation Sound Reinforcement System modeling that's ongoing right now at Treble. Yeah.
Cool. So Diego asks that DGFE solver would require a mass, I suppose. Is it automatically generated?
Right. Yes. So the user doesn't feel this so much. When I hit in the demo, when I hit this estimate simulation button, then there under the hood the mesh is being created. Yeah, so it's kind of automatically generated.
Yeah. So another question from Celia. Do you need high-speed internet the whole time you're working on the software?
You do need an internet connection. It doesn't have to be some ultra high speed connection or something like that, but since it is a web-based tool, then yes.
Yeah. Diego asks, what kind of machines on the cloud did you use in the demo?
Our infrastructure is running on AWS, and the machine that's actually doing the number crunching, running the simulation is an A100 NVIDIA GPU, a single GPU that's running the simulations. We have done lots of experiments where we do multi-GPU simulations. This enables us to go much higher in frequency. You know, we're doing simulations where we use maybe 8 GPUs to do full bandwidth wave-based simulations. This works really well. The solver is so scalable that it can do these kinds of things. But in the web tool that we're offering now, we're not enabling all of these multi-GPU capabilities just yet.
Lewis asks, how high in frequency can we go if we want to use wave-based calculations? Can we calculate the whole range with wave-based calculation to reduce the uncertainty associated with having to guess scattering values for each surface type?
It's kind of annoying, this scattering coefficient, which is a bit of a guesswork indeed. So, as I just said, actually, we can, in principle, cover the full bandwidth wave-based, but it requires quite substantial computing resources, so it's maybe not always the appropriate choice to do that. But you can. But in the tool right now we're limiting the wave-based up to 3 kilohertz, so covering 6 out of the 8 octave bands, I think I'm saying correctly, 63, 125, 250, 500, 1000, 2000, yes. 6, I can count to 6. And then 4K and 8K are always geometrical acoustics. And I don't know if you have some comments on maybe sort of how high it's relevant to go.
It actually depends on the dimension and the Schroeder frequency of the space. If the Schroeder frequency is like 20 hertz, you don't need to absorb the whole space, really the big space, like 30,000 cubic meters up to 20 kilohertz. So it's a compromise, basically. Yeah.
Mm-hmm.
You have to look at the Schroeder frequency first, and of course the treble is suggesting some automatically suggesting some values of the transition. But of course you could actually change the transition frequency, yeah, to test a little bit more for DigiFam simulations.
One idea we've played around with is that you could use the wave-based simulation to estimate the scattering coefficient of some particular surface and then input that into the geometrical acoustic simulation. That's kind of a way you could approach being more precise in the scattering definition.
Yeah, cool. So class asks, does the model support acoustically semi-transparent surfaces?
Right. I guess we touched upon that before. That's coming.
Garðar, do we have different HRTFs to choose from for the auralization?
Yet another good question. Right now, there is just single kind of generic HRTF that goes in the auralization. This is also on our roadmap to enable users to select from different HRTFs or even upload their own HRTFs for the auralization.
Yeah. Daniel, congratulations, Treble, looks great. What about simulations of outdoor acoustics? Is this software only for indoors?
Excellent question. I would say that when building this platform, we were more thinking about the indoor case. It's more tailored towards that, but you can use it as is for sort of smaller scale outdoor sound simulations. We do not take into account, for example, weather effects or things like that, but maybe one thing that would be really nice to have is perfectly absorbing boundaries, so you can kind of truncate your domain to do these kind of outdoor simulations. We do have like very absorbing boundaries, but not perfectly absorbing just yet. So we are working on enabling this. It's maybe in the sort of medium-term roadmap to make it even more tailored for outdoor simulation. But already now, you know, we have had some beta testers that are using it where they have a street canyon. They're testing some facade design and listening to what's the difference if we, you know, change the shape of the facade or if we select some materials of the facade and things like that. And they can listen and test this and so on.
Exciting. How is the cutoff frequency between the wave-based and energy-based acoustics method determined?
Right. It takes into account the geometry of your particular model and estimates the cutoff frequency based on that. It's mostly based on the volume of the space and then also a bit of the sort of estimated reverberation time of the space. I think I'm saying something wrong here. I think it's only the volume it takes into account at this stage, and then tries to give an estimate.
Okay. So Richard asks, can the platform receive models directly from Revit/Rhino or other architectural modeling programs without going through an intermediate program?
Yes, at the moment we would have to go through SketchUp. The Rhino plugin we essentially have already built. We just need to make it look a little nicer and so on, and then it's coming out too soon. Revit is a bit more complex. Revit is somewhat of a beast, you could say. But so sort of medium-term roadmap, 6 to 12 months, we're going to try to have a Revit integration. And then a part of that will be this notion of automatically extracting the geometry, simplifying it so that it's suited for simulations. Kind of try to do this in an automated way to some extent.
Yeah. Ben asks as well, what about imports from Rhino and Revit? But I guess you already answered that. Javier, hi, is SketchUp always needed, or do you offer a room modeling tool?
Right. Yeah, and also like a generic file import is also on the roadmap, so you could, in theory, import for any software from any software.
Kay asks, is it possible to input your own sound clip, perhaps level, calibrated, and EQ'd into the simulation for simulating more specific sound sources?
At the moment, we have a very large database of anechoic sounds that you can choose from. Uploading your own is yet again on the roadmap. It's not a hard thing to do, to be honest, so I think that will come soon. We've also talked about like kind of enabling real-time input, where you could have a mic and like, hello, and then listen to the reverb of the space. But yeah, let's see how that goes. There's latency and things to think about there, but yes. Your own, kind of uploading your own anechoic sounds is definitely on the short-term roadmap.
Perfect. Alexandra asks, how feasible is it to count on high-quality input data for low-frequency part calculation? How do you imagine it would work in practice with the amount of data needed for each model? It is already difficult to have a reliable absorption coefficient for high-frequency data. That is just a very rough approximation. Just to collect the input data for a classroom or a concert hall would be a huge project in itself. Customers of acoustic consultants would not necessarily be willing to pay for the time spent on that.
Mm-hmm. Yeah, excellent question.
I think this is a very difficult question. Of course, I mean, collecting good quality data takes time and effort. And of course, I mean, some people willing to pay or not. I don't know, but I mean, without high quality data, the simulation result is always degraded. So it's a compromise. Without a good input data, you cannot expect a good outcome from the simulation.
So we are really doing our best to address this very real problem that's described here. We built this very large database of materials where we really try to accurately estimate or construct impedances of all these very big database of common materials, which are based on very well-established models and so on. So I would say that this is already a much better approach than using the random incidence absorption coefficients, which are mentioned here in the question. So already we're kind of taking some steps. Then the material generator I mentioned in the end of the talk is an even further step. Then you can sort of model the build-up, the unique build-up that you might be working with. So yeah, we're very much trying to address this very tough problem. Yeah, because indeed, as you say, without good input data, you can't expect good output data.
Right. Yeah. Sylvan asks, would your tool somehow be able to analyze the simulation and show the acoustically problematic parts of the geometry?
Mm-hmm. Yes, you can certainly analyze how the acoustics sort of vary across space and see where problematic areas might be. The tool does not maybe per se highlight problematic areas or automatically suggest improvements or things like that. But you can definitely analyze the sort of spatial characteristics of the acoustics. And this will be then even further enhanced when we get this animation capabilities I also mentioned in the talk.
Yeah. And as a follow-up, would it ever be possible for the tool to propose a solution using this data?
Right.
Yeah.
Yeah. Indeed, something we have discussed many times here at Treble. Yeah, we could definitely look into that, let's say.
Rocky asks, is the energy sources data .gll files?
Yes, that's our goal to support it. This is part of Operation Sound Reinforcement Systems, where we want to support the GLL format because that's kind of industry standard for loudspeakers today.
Yeah. Keto, does your tool include the parameters for open plan offices in ISO 33823? If not, is it something you'd be planning on including in the near future?
Yeah. So not yet, definitely coming soon.
Gilmer, do we put our own audio recordings to get oralized?
Yeah. I kind of touched upon that, I guess, before.
Yeah. Question from Wolfram, does the simulation only support static models? Is it possible to simulate scenes with moving geometric and sources?
That's a fun problem to address. We are working on the moving source problem. It's not entirely trivial, let's say, but so I would say that we are working on that. It's not supported at the moment in the web app. But indeed, we have been getting inquiries about this. I think, for example, for synthetic audio data generation, this is an important feature to have, that you can have moving sound sources in the virtual audio scene. Also for urban acoustic simulations, maybe car pass-by or things like that. So this is being worked on. There was maybe some...
Maybe not moving geometries.
Moving geometry, yes, exactly. That's at least a few years down the road, I think, unfortunately.
Yeah. Next question from Young. Can we take care of the sound source located outside building in terms of boundary condition?
Yeah, indeed. So you could have a space and then a window and then model the surface of the window as a sound source, which is kind of emulating sound coming from the road outside. We have, as I mentioned earlier, we have under the hood already implemented these kind of surface style sources. So they will come soon to the web tool too.
Okay. Klaus asks, is there or will there be support for using your own sound files? Okay, we've covered that.
Right.
Leo, hey, what about CLF files, sources? Can we import them?
Yeah, definitely Operation Sound Reinforcement Systems. So GLL and CLF will be supported for sure.
Thomas asks, is there a possibility to export microphone RA impulse responses, like the ones you simulate for the oralization anyway?
Yes, I love I love simulating microphone arrays. It's such a fun problem. So right now, the web app simulates second-order ambisonic impulse responses, which you can download if you hit the download package button. We have been doing in pilot projects with some of our partners, early adopter partners, ambisonic simulations up to 16th order, where we capture very detailed phase information up to 8 kilohertz. And yeah, these very high order ambisonic renderings or encodings, let's say. So the technology supports it. We are doing it in pilot projects. So if you're interested in kind of exploring this together with us, then reach out, let's say. But getting it into the web tool is also then again kind of on the roadmap. Yeah. And you know, these microphone arrays and these audio devices, having two microphones placed very close to each other, and you want to kind of detail simulate the phase difference between those two microphones in a room or something like that. That's something that we can do really well. It's a very exciting thing.
Yeah. a lot of exciting things happening. So we have a lot of questions coming in, but we only have time for one more.
Okay. We'll try to address these other questions somehow. Maybe we can reach out.
Yeah. So is there also a way to visualize parameters in grids, for example, or other items to investigate acoustical problems in your model, not only with auralization?
Right. Yeah. This is the other top priority at Treble. So one is, so for the shorter term roadmap, one is operation sound reinforcement systems. The other is operation color maps and animations and sort of 3D visual results in the tool.
Yeah. Cool.
Two top priorities.
So that brings us to the end of our time. Thanks everyone so much for your insightful questions, and a big thanks to our speakers, Cheol-Ho and Finnur. Don't forget that the recording will be sent to you later today, and if you have any further questions, do not hesitate to reach out to us, and if you want to learn more, of course. So we'll also be in touch regarding your free trial of Treble. So thank you for joining us today, and have a fantastic rest of your day.